our last topic to focus on with the weather is patterns in climate and how climate is changing. One area of confusion, we've mentioned this before, what is weather versus climate? Weather, again, is the short-term, day-to-day variation in what's going on in the air. For example, do I need my raincoat tomorrow? Will I want to bring my sweater? Those are questions about the weather. Day-to-day variations. And there is quite a lot of variation. Even hour to hour sometimes can be rather dramatic. Climate, in contrast, is the long-term average pattern in our weather. So, for example, you sometimes see people confused about issues, saying something like, yesterday was really cold, so global warming must not be happening, or yesterday was really hot, must be global warming. No, that's weather, not climate. Doesn't tell us one way or the other. Now, if we were to see a lot more warm days and not as many cold days in many parts of the world, okay, that would be indicating global warming. But one warm day, one cold day, that happens. We need to focus on the long-term averages. Another example for around here, what's the weather? Well, right now it's sunny out there. Peeking out the blinds from here in Boiling Springs. But what's the climate for Boiling Springs? Well, we've got fairly long summers that tend to be on the hot and humid side. We've got more variable, typically somewhat moderate temperatures in the spring and fall. And winter, it can get cold. Sometimes we get snow or other frozen precipitation. But we tend to have a few warm days thrown in there in the winter as well. It's kind of up and down. That's our typical long-term average pattern. That's our climate here. That does not tell you whether you need your umbrella tomorrow, but it does give you something of an idea of whether you need to own an umbrella. Around here, all parts of the year have a decent chance of having some rainy days in there. There's a little bit rainier sometimes than others, but our rain's pretty well spread around the year. It's another aspect of the climate. Now, long term, if we look at evidence from the geologic past, there's been quite a lot of change in the climate. And this will continue on into the future. So climate does not stay in one point. There's not one single magic point that's the one good option for Earth. Instead, the real problem is how fast change is happening. Faster change means that people, animals, plants, other living things will have more of a challenge in keeping up, adjusting quick enough. This is a very complex diagram because it changes scale a lot of times, but the basic idea, the ups and downs of this line here represent how temperature averages have changed over the past, actually, about 540 million years. And yeah, there are ups and downs. Here's our average temperature for the recent past. We can see actually most of this time is warmer than today. We're in a somewhat cooler than average time for past 500 some million years at any rate. You've had some really cold times before that. But there are ups, there are downs. Nature does have some variation there. Zooming in at younger things, we have, for example, the back and forth variation that has given us glaciers melting versus advancing. And then zooming in even more, up towards today, right at the end here, we're seeing a relatively notable rise in the temperatures there. So we're seeing increases very recently that are quite rapid compared to your long-term average. Carbon dioxide is a big player here. Now, of course, people have been burning stuff for a long time, but we've really been doing a whole lot of it since getting going with the Industrial Revolution and the associated major use of fossil fuels such as coal, oil, and gas as an energy source. So going along, the more stuff we burn, the more carbon dioxide goes in the air, and indeed, the amount of carbon dioxide we measure in the air has gone up. Today we're actually somewhere around here off the chart that goes only here to close to 2,000. Now, even up here, that's a lot less than the amount of carbon dioxide that we had in the air, say, about halfway between us and the dinosaurs back in the Eocene. So, why worry about there being more carbon dioxide? Earth's had that before. Again, two problems. One, this is a very rapid change, much faster than most geological processes tend to show. So, keeping up is an issue. Also, back then, yeah, we had more carbon dioxide. We had crocodiles living in northern Canada. That is not the world we're used to. That would involve major changes. Likewise, being that warmer, we don't have major glaciers. A lot more water is in the ocean rather than up in glaciers on land. Sea level was a lot higher. Boiling springs would have been close to the ocean, which means all those folks east of us would be awful soggy. A lot of land where people's houses and farms and things like that are would be underwater under those conditions. So, yes, Earth has been warmer before. No, that does not mean that it's a great idea to make the Earth go back to that condition very quickly. Again, as was true in the oceans, up in the air, our main source of energy is the sun. Coming in as light, some UV, that sort of thing. And depending on our surface albedo, it may be either absorbed, warming up the land, and then the warm land releases heat, infrared radiation, that warms up the air. Or if our albedo is high, the surface is very white, most of that light just reflects back, doesn't warm things up. But we have the greenhouse effect. Gases in the air, certain gases, not all of them, are good at absorbing that infrared radiation coming from the Earth, the heat radiation there. And if the gas absorbs it, now that gas is warmed up. That one molecule is zipping around a little faster, and that energy is still in the atmosphere. It hasn't just gone back out into space. So these greenhouse gases, by absorbing heat, hanging on for a little while, they slow the loss of heat from Earth out into space. Also, when they release their heat, not all of it's going straight up. It may go off to the side or even back down. That also would tend to keep that heat in the atmosphere longer than if it's just going straight back out into space, like it would, say, from the moon with no atmosphere. So, although the physics is significantly different, the functioning of greenhouse gases is a little bit like a blanket. A blanket is not in and of itself warm. If it's a cold winter night and you hop under the blanket, it's cold there at first, unless you've got an electric blanket. But after a little bit of time, your body heat being trapped under the blanket stays there, and things get nice and cozy under the blanket. Without the blanket, your heat escapes on out into the room, and you do not warm up nearly as well. Likewise, having the greenhouse gases in the air slows the loss of heat by keeping the heat in the air for longer, and so the result is things are somewhat warmer. Now there are lots of other players out there, and even within greenhouse gases. Different gases have different impacts on the temperature. Some gases really grab heat, absorb it very well, and so even a little of that really warms things up. Others, yeah, they can get some, but they're not nearly as good at it. Don't warm things up as much. Also, how long does that particular gas tend to float around the air? What's its residence time like? Some things, carbon dioxide for example, will tend to float around in the air for quite some time before something else happens to it. So even though carbon dioxide per molecule doesn't absorb nearly as much heat as some of the other gases, it tends to stick around longer. And so over that total amount of time, the effect of carbon dioxide adds up. Others, methane for example, that's more reactive, that tends to get used up faster. It also is a stronger greenhouse gas. If you have the same amount of methane versus carbon dioxide in a jar and expose them to light, the one with the methane will warm up noticeably more than the carbon dioxide one. But because methane gets used up back out of the air sooner, it will have a somewhat decreased impact. So you've got different variations there. Carbon dioxide, methane, these are important natural ones. Water vapor also, the water is evaporating, condensing all the time, so that's a little more complex there.